Okay, we're ready to start on another set of conics. We've looked at circles, now we're going to look at ellipses. Well, we know what a circle is for sure. We've known that since what? Preschool! Let me get a pen color here. Okay, so we've got circles, which you can probably draw better than I can, which have a center. Have a center, and then we've got, I'll take advantage of that dot. We have ellipses, which instead of having a center have two foci, we say. If you take focus, all of you who are studying Latin or have studied Latin know this. That's the singular, and then the plural is foci. So we go from having one focus to having two, takes us from a circle to an ellipse. We're going to be able to find the vertices. The vertices. We'll talk about what the vertices are. We'll have to look at something called a major axis, which goes through the two foci. The vertices will end up being where that axis intersects with the ellipse graph itself. And then we also have co-vertices with something called a minor axis, which is perpendicular to the major one. So we'll talk more about that shortly. Remember this completing the square? We're going to use this so much. You're going to understand why I've been emphasizing it. We take a, I don't know, let's try one. X squared minus 6x. And we figure out what we need to add to that, and it always is an add, in order to get a perfect square trinomial. In every case, we are interested in a perfect square trinomial so that we can put together a binomial squared. Once we have that binomial squared, what do? We take the square root of it. And this will release the x. Right now we've got x squared and x linear. How do we ever get just a single x out of that? This is how we do it. We add some number. And what would it be here in order to make this a perfect square trinomial? We'd take 1/2 of -6, and then we'd square that. Take 1/2 of -6 and square it. That would give us a -3. We square it, we get 9. This then can be factored. We take the square root of that and we end up with x minus 3. Now, of course, there's more to it, isn't there? When we add this 9 on one side, we have to keep a balance. And when we convert to this, it's exactly the same thing, just in a different form. But when we take the square root, we also have to do it to the other side. Well, that's enough of an introduction. Let's go on to reminding ourselves of what we had in our last lesson. We're going to find an equation for a circle which has a center and a radius 2. What was that formula? X minus the x-coordinate of the center squared plus y minus the y-coordinate of the center squared will equal r squared. You need to memorize this. So here is our x-coordinate of the center, also known to us as h. X minus 9. right? We have a positive 9, so it's minus 9, plus y minus the y-coordinate of the center equals the radius squared. We know the radius is 2, so there we are. We have it. This one, find the center and radius of the circle. So if we are really familiar with this, we don't have any trouble. Minus whatever our h is. Well, minus a positive 10, so our center has to be 10 as our x-coordinate of the center. And y minus a negative 3 is the only way we'd get this. Y minus a negative 3. So this must be a negative 3. It's equal to r squared. So we take the square root of this, and we know that r is equal to 10. Find the center and the radius of the circle. Ooh, this one is calling for a little more activity, isn't it? Ooh, because we don't have it set up in the form. Let me write the form up here again. X minus whatever is the x-coordinate of the center. Square that. Y minus the y-coordinate of the center. Square that. So we want to convert into this. We can take this piece, add a constant to it, get a perfect square trinomial, and then convert it into this. This one, same thing for the y. Let's try it. So I've got x squared plus 12x. And I know it's always an add. I'm going to add something there. And then we're going to have plus y squared plus 4y. See, I'm not actually doing anything yet except copying it with enough space so that I can form those perfect square trinomials. What would I need to add here to make this into a perfect square trinomial? Half of 12 squared. Very good. Oop, I'm out of balance. Whew, I'm back in balance. How about this one? Another perfect square trinomial. I take half of this and square it. Ah, out of balance. Back in balance. This becomes x plus, right, this is a plus, and the square root of this, x plus 6 squared, plus y plus 2, right, the square root of this, plus comes from here, equals, ooh, what a mess this is, 49. So, just by doing that, I know where my center is. My center is at x minus h. My center is at minus 6. Y minus k. Minus 2. That's my center. And my r, this is r squared right here. Okay, that was a little review. And we're already 9 minutes in. Wow. Oh, ask me to do this paperclip thing. We'll do that in class if you ask me to do it. All I'll be doing, if we do that in class, is demonstrating how an ellipse is formed. We have one focus here and another focus here. They are the same distance from the center. Actually, we're going to call this distance, you'll find out later, we're going to call that distance C, from the center to the focus. And then we've got an ellipse. If I took a string and tacked it into each of the foci, as I move my string around, keeping this taut, it would form an ellipse. That's what I'd love to demonstrate in class. The definition of an ellipse. It's a set of all points for which the distances from two fixed points, known to us as sum to a constant, and that constant are these two distances here, the length of the string. Okay? That is the definition. Skip over that. The ellipse. So we know that this distance here from one focus to a point on the ellipse, and the other distance going from that point to the other focus, it stays constant. It turns out that it is equal to 2a. And when we say a, we're talking about, how can I mark it so it's easy to tell what I'm talking about? We're talking about this distance from there to there. That's my a. I have another distance that I'm very interested in, and that goes from the center again to the ellipse. It's perpendicular to the major axis. We can always figure the major axis because it's the one that is longest, and it goes through the two foci. If we want to know the length of the major axis, what do? We just double what a is. If we want to know the length of the minor axis, we just double this b, 2b. Okay. Now, I'm going to tell you how we can figure out what c is. C can be found by using this equation right here. You take whatever the length of a is, remember a is from the center to this point on the ellipse. This is where the major axis hits the ellipse. That distance is a. So you square that distance, and then you subtract the distance from the center along the minor axis to the ellipse, square that distance, and you subtract it. And that will give you the distance that the focus is from the center. So that's a very important piece to remember. What is the length of the major axis if a equals 4 and b equals 3? Remember now, a is from here to here. Well, make it fat enough. This distance here is a. You notice a is always longer than c. I should mark this one too. What is the length of the major axis? A is equal to 4. And the major axis goes from here to here. So right? This is a general formula for quadratics. We've got an x squared, we've got a y squared, we've got an x to the first power, a y to the first power, and we have a constant. It's been set all to 0, so it's in a standard form. You'll notice we also have an xy. You will encounter this in more advanced math classes. We're not going to have any equations that have b equal to anything other than 0. We will always have b equal to 0. What does that mean? That means you're not going to see this term showing up. In an ellipse, oh, wait a second, let's go back. In a circle, what did we know was true about A and C? They were exactly the same value. In an ellipse, A and C, the coefficients on x squared and y squared are going to have different values and the same sign. So let's take a look at this one, and we're going to transform this equation so that we can see what the lengths of the major and minor axes are. You're going to find this so helpful. The way we do this is we're going to force this equation to equal 1. We want an equivalent equation. How could we do that? Well, we'll have to divide everything, all terms, remember? What you do to one side, you have to do to the other side. And if you've got more than one term and you're dividing, you've got to divide all those terms. So we end up with x squared over 225 divided by 9 plus y squared over 225 divided by 25 equals 1. And I promise you we're going to be able to see what the lengths of the major and minor axes are before we finish. What did I do here anyway? I took this 9, which was in the numerator, and I divided within the denominator. I didn't have to do it that way, but because what could I have done? I could have said, okay, let's factor a 9 out of this. If I divide 225 by 9, what do I get? That's right, I get 25. And over here, if I factor 25 out of 225, these will cancel out then. I'll have a 1 up here, and that's right, a 9 down here. I always want to have a coefficient of 1 on these squared terms. And you'll notice that this is going to do exactly the same thing. So I get x squared over 25 plus y squared over 9 equals 1. Now my magic is about to come in here. The length of my major axis is associated with whichever of these numbers is larger, and the minor one is associated with whichever of these is smaller. Just like we took the square root of r squared to find out what the radius was, we're going to take the square root of this to figure out what the major axis is. So if we wanted to think about it in a general form, I would write it like this. So what is my a? Well, a squared is 25. So my a is 5. And my major axis, it's 2 times that, or 10. My b squared is 9. So my a is 3. Oh, what am I saying? My b is 3. Sorry. My b is 3. And 2b is going to be 6. So this always works every time to figure out what is your major and minor axis. So this is what we did. The right member, I'm talking about this, has to be 1. We figured out how to do that. We divided everything by 1. The coefficients of the numerators of these terms over here in the left member, they have to be 1, and we figured out how to do that. So this is the first step. This is just reviewing what we did just a moment ago. That made this equal 1. And then what did I do? I said, okay, y squared over 225 divided by 25. So I got the coefficient of my y term to be equal to 1. And I did the same thing with my x. 225 was in the denominator now, and then I divided by that 9. Here's the general equation of an ellipse. Looks a little familiar, doesn't it? Something like what we saw for a circle. For a circle, it's x minus h plus y minus k, where we're talking about the center as being hk equals r squared. Now things have changed in that we force this to be a 1, and we have underneath here the lengths from the center. Here's our major axis, the length from the center to the ellipse, and for the minor axis, right along here. The center is HK, just like a circle. So the focus is no longer at the center, but we use the center in our general equation of an ellipse. We're going to go through some examples of that. What am I seeing right here? I should mention that in this one, I would be applying the square to the numerator and the denominator. The way, another way you'll often see this written is x minus h squared over, let's say, a squared plus y minus k squared over b squared equals 1. This works when the major axis is going this way. We'll talk in a minute about what you do when it goes this way. Of course, when the center is at the origin, your h is 0, your y is 0, and you get something that looks a lot similar. It is similar, and it's simpler. And that would be x squared over a squared y squared over b squared equals 1. All right, so look at this mess. Oh my goodness. Can we do anything with it? Of course. We've got this y and this y we can put together. You know what we're going to do with them, don't you? We're going to try completing the square. And then we've got, let's get it over here, 49x squared. And we're going to take, so I got that one. And now we're going to subtract 196x. What a mess that is. So I got that one. And now we're going to say, look, I'm leaving space. Why is that? That's right. We want to complete the square. It's going to be quite a job. 9y squared plus 72y, and I'm going to leave some space. And I'm going to add 101 to both sides. So I'm going to have a 101 right here. You don't mind if I delete this, do you? That's our answer. We'll get to that in a minute. I just know I need a lot of space. Well, completing the square. I do not want to try completing the square when I have a coefficient of 49 on here. So I'm going to factor out that 49. Regardless of what I get for a mess in here, I cannot have anything other than a 1 here. Fortunately, when I divide, let me try the x squared term. When I divide 196 by 49, look at this lovely number I get. Isn't that nice? Let me set this other one up as well. We'll get back and complete the square in a minute. Again, I do not want this 9 for completing the square, but I have to hold on to it, of course. When I divide this by 9, so this is looking much better already, isn't it? We organized our x's together, our y's together. We factored out the leading coefficient from both these terms. Now I'm just going to look inside and figure out what I need to add here to make this into a perfect square trinomial. That's right, a 4. Out of balance, seriously out of balance, because I not only added 4, I multiplied that 4 by 49. So that, what did I do? I added actually 196. So I better fix that quickly before the ship sinks here. There. Now we're back in balance. This one. Take half of 8 and square it. Plus 16. Okay. 16 times 9. Is that right? Oh, no, it's not. 144. Sorry. So I added 16 here, but it's multiplied by 9. So what did I effectively do? Added 144. I got to get it back in balance. Well, this is something I better add up right now. 101 and 196. We'll add those all up. I get 1, carry 1, 4, carry 1. Oh, that looks terrible. Are you kidding me? Yuck. 441. Maybe I made a mistake. Just looks awful. Okay. So now I've got 49. And the reason I did this perfect square trinomial was so I could get to something like that. Plus, again, perfect square trinomial so I could get to this. Oh, that's not. Undo that. Okay. So I've got, this is a minus, this one is a plus. This is x minus 2. This one is y plus 4. How did I get those? My sign matches whatever the middle term is. Okay? And this is simply the square root of my constant. I'm going to have to force this to become 1, which means I'm going to divide this and this. All the terms on the other side have to be divided. What do I come out with? Well, I could write it like this. And I could write this like this. If I divide 441 by 9, let's see what happens. Oh, you've got your calculator right there. I never have my calculator handy. I'm so sorry. So 9 would go into this. Let's see. Not 6, not 5. Only 4 times? Okay, 36. I'm thinking I made a mistake. Oh, maybe not. Oh, this is fun. Oh, this is great. Or is it? Okay. So that tells me, I'm going to extend this page some more, that I've got y plus 4 squared over 49. And that actually reveals for me what this has to be too. Because 49 times 9 equals 441. If I divide this by 49, I get 9. I thought it was such an awful number, this 441. Turns out it's a beautiful number. I love it. So, oh, look at this. My larger number is with y, so my major axis is going like this. Well, it's actually going straight. But you know me and drawing lines. So I've got an ellipse that's shaped like that. And my center, where's my center? My center is at 2 and negative 4. Where am I getting that? I'm reading it right off of here. There's my h, the 2, and minus my k means this must be a negative 4. What is my a? In this case, this is my a square. The larger one is always your a square. Smaller one is the b square. So I know that this distance from here to here is a equals 7, b equals 3, and what does c equal? Well, c squared is easier to start with. It's going to be your larger one, a squared, minus smaller one, b squared. So that's 49 minus 9. So C is equal to the square root of 40. When you're graphing, it's going to be extremely important for you to go ahead and figure out what that is. It's going to be 6 point something. It will always be smaller than A. So if you come out with something here that isn't smaller than A, you've made a serious mistake. Okay, so we figured out what the center was. It was at, let's write it down, 2, -4. We'll go ahead and graph it on a coordinate plane. Notice that these are 2 by 2 grids. So I go over 2 for my x and down 4 for my y. Right here. That's my center. And this has its major axis, the larger number on y, so it's vertical. So I'm going to go 7. This is 2, 4, 6, 7. Here's part of the ellipse. And 2, 4, 6. Oh, I have to, yeah. And then my minor axis, which is going to be perpendicular to the major one, is 3. So I'm going to go 3 away from the center. 3 away from the center. Now you see, this makes it nice. I've got, like with a circle, you go east, west, north, and south. You get those 4 points, and it allows you to sorry, such a terrible looking. You know, if it really looks as bad as mine, it probably is a good idea to write in that it's an ellipse, because nobody's going to look at that and know it is. So there's my center. I've graphed it. And it did turn out to look like that. Well, when I did it previously, by hand, it didn't look too good, but that's what I've got here, the sketch of that ellipse. Plot the foci. Ooh, how do I figure that? We already did, didn't we? It was the square root of 40, which is going to be 3 point something. I wish you were here with me to tell me what it is. What am I saying? 3. Sorry. It's 6 point something. Sorry. I know that because the square root of 36 would be, and so it's between 6 and 7. Closer to 36. So I don't know. Let's say it's right about here. I can't draw this very accurately anyway. So it's right about here. Just a little more than 6. I'll just make a big dot. That'll cover all my inaccuracies. Would not have covered this being a 3, however. That'd be clearly a mistake. So we know how to find the distance the focus is away from the center, right? A squared minus b squared. So this is the general equation of an ellipse. When the center is at the origin, you can write it this way. Here's how you find your foci, and that's it for today. I'm sorry the lesson went a little long, 39 minutes, but wasn't it worth it?